rational exponents. So rational exponents is just a fancy way of saying exponents that are fractions. We're going to start with fractional exponents that have 1 in the numerator. So if I give you something like this, we just have x to the 1 over n, where n is some number. This means the same thing as the nth root of that number. Okay, so let's put numbers in here. So let's say I have 2 to the 1/3 power. What this means is you are taking the cubed root, or the third root, of 2. Okay, these two things are the same. So that means that we know the square root of 16 is 4. But another way that I could write this is 16 to the 1/2 power is equal to 4. Okay, so these are the same things. You might wonder why, why do we have both? And it's because fractional exponents do arise sometimes through the course of doing other operations with exponents. And it's useful to be able to work with them because if I'm just trying to do something with like a root, right, where I'm suppose I have like 2 to some power divided by the square root of 2, there's nothing I can do to simplify these, right? But if I turn this radical, radical is the word for the kind of root symbol. If I turn this radical into an exponent, then suddenly I can use my exponent rules, right? I can subtract this minus whatever the thing is here. So it kind of unlocks more simplification ability when we're working with expressions. So real quick here, let's try, have you try one. Try 27 to the 1/3 and try 100 to the 1/2. So pause the video and do each of those. You should get, this is the same thing as the cubed root of 27, which is equal to 3. And this is the same thing as the square root, right? Or you don't have to put the 2 there, but square root of 100, which is equal to 10. Okay, so that's how you deal with rational exponents when this is just a 1, right? When the things up here are 1, there's nothing in the numerator. It changes a little bit when you have something in the numerator, okay? But it doesn't get that much worse, right? So suppose I have, instead of 27 to the 1/3, I have 27 to the 2/3, okay? Well, remember, much earlier on, when we were learning about kind of the rules of exponents, we said that a power raised to a power, an exponent raised to an exponent, we can multiply those, right? But I can also do the opposite, right? I could say, 8 to the 4th power, this is just equal to 8 squared, right? Because 2 times 2 is 4. So I can factor this number into, factors and split them up by parentheses, and that's like a totally legal, fine thing to do, right? So if I think about, could I do that up here? I can, because I know how to deal with the 1/3, and I know how to deal with just squared. 2/3 together is what's a little tricky. So let's split it up. Let's turn this into 27 to the 1/3 squared, right? So make sure you understand this piece, because this is the justification for everything we're going to kind of shortcut going forward. It's why we're able to do what we do, because then I can rewrite this as, well, 27 to the 1/3 is the cube root of 27, and then I just have that whole thing squared, right? So the cube root of 27, as we said on the previous page, is 3, but I have 3 squared, so that gives me 9. Okay, so when you have a fraction like this, so you have 27 to the 2/3, right? This is our base that hasn't really ever changed. This is our exponent, right? That we're like going to raise it to a power. And this is our root, right? We're going to turn that into our root. This just stays, the 2 stays as an exponent, the 3 turns into the cubed root of something, okay? So I'm going to do another one, and then I'll give you a chance to try a couple. So let's say I have 64 raised to the 5/6 power, okay? So I see this, and I say, all right, I have a fractional exponent here. The numerator is not a 1. I would like to split this up. So I'm going to turn this into 64 to the 1/6 raised to the 5th power. And once I'm here, right, I can write that as the 6th root of 64 raised to the fifth power. Okay. And then, I can look at a table, or if you're really comfortable with powers of 2, you can just kind of think about it. And you say, okay, the 6th root of 64, a number I have to multiply by itself 6 times to get 64. That's going to be 2. And I still have the fifth power here. So then you can go through and you can check your tables, or you can do it out. 2 to the fifth should give you 32. So 32 would be your answer here. Okay. So go ahead and try this one. Try 100 raised to the 3 halves. So pause the video now and give that a shot. You should find that, again, we're going to say, okay, I have a fractional exponent. The fact that the 3 is bigger than the 2 doesn't change anything. I know so far they've all been smaller. The fractions have been smaller than 1, and this time it's a little bit bigger, but you do the same process. So I'm still going to write this as 100 to the 1/2 power raised to the 3rd power. And then this turns into the square root of 100 cubed. So square root of 100 is 10, and I have 10 cubed. 10 times 10 is 100, times 10 is 1,000. So 1,000 is my answer here. Okay. You can split these up in like the opposite way, where you could say, I'm going to write 100 to the 3 halves. You could write this as 100 cubed to the 1/2. And then this gives you the square root of 100 cubed. Okay. Now, this one isn't super useful when you are evaluating roots of numbers, right? Because 100 times 100 times 100 is very big, and that's like an annoying computation to do, and then having to calculate the square root of a really, really big number like that is also kind of a pain. So we prefer to do the root first, right, and then raise the smaller number to a power that makes it bigger, as opposed to make the number huge and then take the root of that. But when you are working with algebraic expressions, sometimes you will want to do this. Sometimes you will actually want to put your powers inside the root and evaluate it after that. Okay. So that's rational exponents, and in our next video we're going to look at scientific notation, which is a nice way to represent very large numbers or very small numbers.